This is the first organic mechanism that most of you will learn for your A-level chemistry, and that is nucleophilic substitution. Now, before we get into the mechanism, let's make sure that we know what these words mean because they tell us what's happening, right? Substitution, we know already just from, the English language, to substitute or to swap. And then nucleophilic, if we just kind of take that apart, nucleo being our nucleus, which is positively charged, and then philic, loving, so nucleus, loving. Now, that's not the formal definition. If we want to define what a nucleophile is, which is going to be the species that's involved in our nucleophilic substitution mechanisms, a nucleophile is an electron pair donor, right? Which makes sense. If it's got that extra pair of electrons, then it's going to donate it. It's going to be attracted towards something that is positive. It's going to love something that's positive to give away those negative electrons too. Now, there are a few key examples of nucleophiles that you're going to see over and over again in your A-level chemistry. The most common one will be your hydroxide ion. Now, the way I'm going to write this is slightly different to what you might be used to in your balanced equations. I'm going to put the negative charge over here by the oxygen because the oxygen, that is where the electron pair or the lone pair that is going to be donated, that's where it is found. Right, that's its position. So I'm going to put the lone pair on the atom where you will actually find the lone pair. The other nucleophiles that you might see, you'll see ammonia, NH3, where we have a lone pair on our nitrogen. You will see cyanide ion, Cn-. Actually, I'm going to draw it out. The cyanide ion, which is Cn-, but it's C triply bonded to another N. Now, again, where the lone pair is, it's on the carbon. And so I'm going to put the lone pair here, and I'm also going to put the negative charge there as well. Other nucleophiles that are not necessarily going to be so important for this particular mechanism, for reasons that will become clear very shortly, are our halide ions. So our fluoride, chloride, bromide, iodide, X-, because again, we've got 3 lone pairs on each of those ions, but we only really care about one of them. So if we put that together, we've got a nucleophile, which is an electron pair donor, which is going to swap with something else. That allows us to start to put our mechanism into place, because the species or the functional group that we're going to see this mechanism with is, where should I write this? I'll write it down here. Halogenoalkanes. Right? And halogenoalkanes are of the form RX, where R is your alkyl group, right? So just your carbon-hydrogen chain or cycle that's not aromatic, but you haven't met aromatic compounds yet in year 12, so it's fine. And then X is going to be your F, or really, when it comes to here, it's really going to be your Cl, your Br most commonly. Sometimes you might see your iodine used there as well. So if we're thinking about nucleophilic substitution, what are we doing? We are swapping the halogen, substituting the halogen with a nucleophile. It is as simple as that. So if I were to write this as kind of a general equation, I would take my halogenoalkane, Rx, I will add my nucleophile. Now for this general equation, I'm only considering my negatively charged nucleophiles. Okay, I'm going to put an asterisk by the ammonia, which has got no charge, it's neutral, and I'll show you that particular example towards the end, okay? But let's say we've just got a negatively charged nucleophile reacting with our halogenoalkane. We are going to substitute, so we're going to end up with R now attached to our nucleophile, and then we'll now have X-, where X- is Cl-, Br-, I-. Now, what does this look like in terms of the mechanism? I'll show you a couple of examples. I'll show you probably the most common one that you're going to see, which is with your hydroxide ion. And then as promised, I'll show you with the slightly stranger neutral ammonia. So let's break this mechanism down with a super simple example. So we've got 2 actually, no, we don't have two chloro anything. We've just got chloroethane, right? There's only one chloro group, so we don't need to number it. Chloroethane, and we're reacting that with the hydroxide ion. The hydroxide ion, this is, of course, our nucleophile, our electron pair donor. This hydroxide ion came from, most likely, the reagent sodium hydroxide or potassium hydroxide, for example. And the conditions for that is it would need to be aqueous, so dissolved in water. And these conditions are important, and I'll explain why in a bit more detail in my elimination video, which is going to come after this one. Okay, so we've got our aqueous sodium hydroxide or potassium hydroxide, which is going to be the source of our hydroxide ions, which is our nucleophile. Now, where are we going to put our curly arrows? Well, it starts to make a whole lot more sense if we put in our dipoles, our partial charges. The halogen, so chlorine, is much more electronegative than the carbon, which means it's going to pull the electron density towards itself while in that covalent bond, meaning that the chlorine or the chloro group is going to be partially negative, leaving the attached carbon partially positive. Now, once we've put those partial charges on, the curly arrows can only really go in one sensible place because we know that opposites attract. Our electron pair donor, or our electron pair, our lone pair on our hydroxide ion with the negative, the high electron density, that is of course going to be attracted to the partially positive carbon atom because, again, opposites attract. High electron density with our nucleophile, low electron density with our carbon. So our first curly arrow will go from the hydroxide to our partially positive carbon. Now we know, or if you don't know, now you know, that curly arrows represent a pair of electrons, the movement of a pair of electrons. So once this lone pair, this electron pair, has attacked this carbon, that means it's forming a new bond with that carbon atom. And if it's forming a new bond with that carbon atom, that would give that carbon 5 bonds, which it does not want, which means that a bond now has to break. And which bond is going to break? Well, the weaker and the polar bond, which is our CCl bond. So our second curly arrow is going to start from the CCl bond because there's another pair of electrons in that bond. And those are now going to go onto our chloro group. And then that is breaking that bond. So now, what do we end up with? Nice and simply, if I just draw the rest of the compound, we're now going to have the Cl has been substituted by the nucleophile. And because this Cl has fallen off, along with its electron plus an extra electron from that bond, we're now going to have Cl minus that's been formed along with it. Now, so that we can really clearly track the electrons, if you really wanted to, we can see that this chloride ion would have a lone pair, the lone pair that was once in this bond. Now, both of those electrons have gone onto the Cl, giving this that lone pair or the electron pair as well. Nice and straightforward. And for AQA, that is as far as the mechanism has to go. For other exam boards, you might look at SN1, SN2. AQA, it's as simple as your lone pair is attracted to the electron deficient or partially positive carbon, which then causes the CCl or the CX bond, causes the CX bond to break, and then we end up with our halide ion. And that is essentially it. Now, as I said before, slightly different if we have a neutral nucleophile, and the one that you're going to see the most often, am I lying? No, I don't think I am. The one that you're going to see most often is ammonia as that neutral nucleophile. So let me do that example next. Okay, for the second example, I'm using the skeletal formula, okay? And again, you will thank me later, okay? It is so much better to get really nice and comfortable with skeletal formula early with some nice simple mechanisms, because later on, you're not gonna have too much of a choice. So let's get comfortable with them together. So we have our skeletal formula where each of these vertices represents a carbon. So just super quickly so that you're all with me. So this would be one carbon, this would be another carbon, this would be another carbon, and they all have the maximum number of hydrogens attached. So this one would have 3 hydrogens attached, this one would have 2 hydrogens attached, this one would have 2 hydrogens attached. Okay, so hopefully you can see how this relates to like the displayed formula that we used before for chloroethane. This is now 1 chloropropane because we've got 3 carbons. Okay, hopefully we're clear here, but I will make another video on different types of formulae, skeletal formula, to make sure you're super confident. Now, once again, same principle applies. The carbon atom, so this one here, that is attached directly to our halo group, is going to be partially positive, as the chlorine is more electronegative than the carbon, so it's pulling the electron density towards it. Because of that, let me just get rid of these now. I don't like them, no offense. Okay, so now we can see quite clearly that our first curly arrow is going to be from the lone pair of the nitrogen on the ammonia to the partially positive carbon atom. And just like before, that would give that carbon atom too many bonds, meaning that we would need to break that CCl bond by moving the pair of electrons from the bond onto the chlorine. So simple, so nice and quick. Now, what do we end up with? Just like before, we have substituted or swapped the halo group for the nucleophile. So we've got now NH3 and we've got our Cl minus with that lone pair from that bond. But, and however, this nucleophile was neutral, right? As opposed to being negative like the ones before. That means that now that this nitrogen has made an extra bond with that carbon, it's now going to be positively charged. So this is actually going to be NH3 plus attached to that carbon, which is not what we want, right? We want our neutral final product. So before we actually get to our final step, or in order to get to our final product, we're going to need to deprotonate our ammonia. We're going to need to remove a proton or an H+. The way that we're going to show that is, instead of just writing NH3 like this, I'm going to draw out the 3 NH bonds. Okay? And in order to get rid of this positive charge on the nitrogen, we need electrons to go back onto the nitrogen to essentially cancel out, balance that charge, which means we're going to get a second curly arrow, actually, well, a third curly arrow technically, from one of your NH bonds, doesn't matter which one, they're all the same, from one of our NH bonds back onto the nitrogen, to show that the electrons from that bond are now essentially cancelling out the positive charge on the nitrogen. Now, that doesn't really just happen by itself. Really, the way that that H falls off is a second ammonia molecule comes along, acting as a base, and steals, takes that H+, and so that's how that bond breaks and the electrons go back onto the nitrogen. Now, what do we end up with as our final product? We end up with our amine, which you'll meet in more detail in year 13. Unless you're already in year 13, then you might have met them already. And you will have NH4 plus from the NH3 taking that H+, and you will have that Cl minus, which we can actually technically just write all together as ammonium chloride. Okay, now, full transparency, you don't, if you look at your mark schemes, you do not have to include this second ammonia taking that H, okay? The only curly arrow that you must include in this, in this next step here is this one, where we're breaking an NH bond and giving those electrons back to the N, right? That is super important. This one, showing the NH3 actually doing that for you, is optional. So if you don't include that, not the end of the world. I think it's good practice too, because it actually shows you clearly what is going on, but you're not going to lose marks if you don't put it in there. If you haven't put this second NH3, then of course, instead of NH4 plus being produced at the end, you would end up with just H plus and Cl minus, right, from this H falling off. And so instead of NH4Cl, you would just have HCl. Okay, both of those options, perfectly valid. I prefer the first option, but hey, I can't stop you. I really cannot. So hopefully you can see here, nucleophilic substitution mechanism, nice and straightforward, only really two options. One, the simplest version when you've got your negatively charged nucleophile, like the first example we saw with hydroxide, and the second example if we have a neutral nucleophile like ammonia. For more mechanism practice and general just A-level chemistry practice, make sure that you have subscribed, make sure you've liked the video, comment if you've got any questions, and I will see you in the next one.